chat. With that said, let me jump into it. So this is a webinar about wearable biosensors. Just to kind of say this won't all be talk. I do have in front of me some technology, so I will be doing some live demonstrations and also just discussing wearable biosensors as well. With that said, let me go forward with these slides. The slides are just to kind of give context, and I think sort of the discussion and the demos will probably and hopefully be the most interesting thing. With that said, so today I'm talking about wearable and implantable biosensors. They'll be talking about trends in biosensing. I will also be talking about why I am here in terms of, how can I put that? In terms of electrochemical biosensing, also a technology demonstration, configurations of biosensors. So when I talk about configurations of biosensors, we'll be talking about transdermal sensors, microneedle sensors, sweat sensors, and also implantable sensors. And we'll also be talking about case studies, a case study of an implantable sensor, a case study of a microneedle technology, a case study of a reverse iontophoresis sensor, and also some case studies from the past about when people try to use bioimpedance for measuring glucose, and also what's currently happening at Apple. But so there's quite a lot to get through. So I'll talk quite fast, but it's really just to kind of get a lot of content across quickly. So when I say why are we here, I think one of the most successful biosensor modalities in the world is electrochemistry. There's probably hundreds of millions of biosensors being used today for measuring glucose in diabetics, and that kind of technology has translated now over to wearables. Just to put some kind of context on that, I'll just share this screen for a second and just say that, here I have the kind of glucose strip. This is the kind of technology that really kind of started developing in the actual 1980s and then was kind of coming onto the market in the 1990s. And this was a really successful technology for quite a few companies like Johnson & Johnson, Abbott, and I would also say Johnson & Johnson, Abbott, and Roche. They were kind of leaders in this kind of technology. But it does demonstrate very well the kind of attractiveness of why electrochemistry is such a good modality for actually doing detection. I mean, electrochemistry can be, so my blood glucose at the moment is 113 milligrams per DL. That's just because I had breakfast. So typically glucose readings would be something like 90 mg per DL. So I'm sort of 23 over, but hopefully that's just due to my breakfast. The reason I bring that up is because it's a good demonstrator of why electrochemistry is a good modality, because in fact, I could do that kind of demonstration live. It's fast, it's reliable, it's actually low cost, and also the sample prep was extremely minimal there. There was no sample prep required, and that's what really differentiates electrochemistry often from optical systems. And it's also the fact that these kind of, if people can get to scale, these kind of glucose strips can be very low cost. It can cost like 5 to 10 cents to make a strip like this, but yet they can go retail at like 50 cents each. So even today, they say that the market's become commoditized, but there are still plenty of people trying to get into that market. But it's a very much, as I say, a kind of commoditized market. Now, the kind of same technology now is translated across to CGM, continuous glucose monitoring. The form factor looks very different between a blood glucose strip and a CGM. And I realize that people are starting to use the term iCGM now, and I think they just mean the I for interstitial continuous glucose monitoring. But I tend to use CGM because I suppose for a while there it was all interstitial, and now people are trying to bring claims out about non-invasive. I'm not sure how really reliable non-invasive is. In fact, the FDA is not very convinced, I would say. Now, the reason that we're talking about wearables today is really because it's really part of a general trend, which was, 2 decades ago, everything was centralized. Smaller instruments actually started to appear in the 80s. handheld devices were definitely appearing in the 80s. We had these kind of palm-sized instruments in the sort of 90s, and now we got to wearables in the CGM, continuous glucose monitoring. I think the first one to launch was probably Dexcom. That was probably around 2005. So we're almost, we're 2 decades in now, even on CGM. And now we've even got to implantables. There's Sensorion, just make a Sensionics rather, is doing an implantable sensor that's also on the market as well. So the general trend, that's driving all this is people want to miniaturize and people want to decentralize. So I suppose that the point is, it's not because people want to have small wearable sensors, it's just that they're adding value. Now, particularly that case, that added value is easier to make in diabetes, where if somebody goes hypoglycemic, they can immediately have health problems. So committing to wearing a iCGM there is an easier business case to make. I can see people working on cortisol sensors at the moment. Cortisol is going to be a particularly tough one for when it comes to wearables, but it is something that we're working on at ZP. And also we're doing quite a lot of work on lactate as well. But with lactate, I think there's 2 applications for continuous lactate monitoring. There's probably sports and wellness, and then there's probably things like sepsis. So at ZP, we kind of have 2 platforms. And if I can just give a bit of advice, there's a point of care diagnostic platform, and there's also a wearables platform. In life, at the moment, BioLink, there's a company down in San Diego called BioLink. They're making a technology quite similar to this, actually. It's they're not doing it on the wrist as a watch format, but they are using microneedles. So this is a microneedle technology. If I can get it onto my wrist. Now, the reason I bring it up is because they're doing a wearable technology. So far, in the last 4 years, they've raised. So they do a patch like this, but it's rather than being what we call a filament, which is what Abbott is using, they're actually using less invasive microneedles. But they've raised $158 million to do this in the last 4 years. I was estimating that Dexcom had spent something like $500 million getting their technology to market, and that was about 20 years ago. But actually, I've had people give me an opinion on LinkedIn that actually it was more like $1 billion. Now, the reason I bring that up is because if your plan is to make a wearable, reliable biosensor, you've got to have significant amounts of funding. Even if you're using technology stacks from companies like Zimmer and Peacock, this is not a low-cost effort. Now, point-of-care diagnostics, depending on what you're wanting to achieve, point-of-care it can be an order of magnitude easier than trying to do wearables. And in fact, I can almost demonstrate that just by doing a quick demonstration. So the demonstration I'll do is I'll take our point-of-care platform. So our point-of-care platform is designed to really allow people to have an idea, that they want to detect something. They would normally have to kind of go away and build the electronics. So I'll do a whole demonstration where I'll take our app, I'll drive the hardware. The hardware will record the raw data. It'll give the data back to the app, and then it will actually send the data to a cloud system called Julie, and actually I'll get a result on my phone. So rather than me just talking about it, so I'm going to do a quick demonstration, and there'll be an involvement of hardware, sensors, an app, a cloud system, and a result on the phone. So let me stop sharing that for a second. Let me go to here. So hopefully you can see my screen. So I'm trying to say here that wearables are about 10 times harder than point-of-care diagnostics. Now at ZP, we can drive our wearables or our point-of-care diagnostics from the same technology stack, but it is easier to do point-of-care diagnostics. So if I can take this sensor, I can click it into this particular device. I can close this up. I've got an app on my phone, which is in Bluetooth connection with that device. I'm going to take the sample. This is the earlier on. This is the sample I'm testing. It's literally more solid than it is liquid, but there is a liquid in there. But this is a good reflection on the power of electrochemistry. That quite a dirty suspension like this can actually be electrochemically analyzed. Also, electrochemistry is very good because actually it doesn't take much sample. So I'm going to put 50 microliters onto this sensor. 50 microliters is kind of akin to a drop of blood. So here it goes. And I will now run the assay. Oops, start measurement. And so what this is now doing, so I've got the sensor in there. The smartphone is in Bluetooth connection with the device. The smartphone tells the device what to do. The device now is running it. When I say device, this is actually a fully functioning potentiostat, but we've also able to turn it very rapidly into a point of care diagnostic. So if our client has a kind of new target analyte that they want to, I don't want to say go after, but something that they want to detect, then we can do it using this particular technology stack. Now, what I'll also do as well, while that's just finishing there, is I'm just going to share you a cloud system. So if I share the screen here, here we go. So we have a cloud system called Julie. And so any kind of time we do an analysis, then the data finally goes up to the cloud. So I've got a result on my phone. So I will just share this for a second. Right. So I've got a result of 141 milligrams per gram. So I'll just hold that. It also says upload complete. So if I just do a quick refresh on this, then I can see a sample with today's time and date, because that's the one I just ran. And then I actually get the raw signal in the cloud. I get the results that I just saw on my smartphone. I also get the raw signal in the cloud. This is a very powerful platform from going from an idea or literally a lab experiment to something actually very tangible, like a doctor or nurse can actually get a result on their phone. I'm going to sort of stop this in a minute, but what I'm saying is it's much easier to achieve this as a point of care diagnostic than it is to take any kind of assay and convert it into a form factor like this, where actually you've got a biosensor, you've got a wearable electronic set, and then we, for example, with electrochemistry, we often have to get into things like the interstitial fluid or the sweat, and you've got all sorts of continuous monitoring, all sorts of movement artifacts due to people wearing sensors. It's a lot harder, a lot more testing is required. So I just did that quick demonstration, but it was just really to make the point that if it was point of care, point of need testing, it can do it quite quickly. If it's wearables, just look at the example of Dexcom, $1 billion to get to market. BioLink so far, $154 million, and they're not quite on the market yet. That app that I was just showing, by the way, it is downloadable off the Google Play Store or the Apple App Store. Unless you've got the hardware, though, it's not so useful. But it just shows you that these things are already distributed. And we basically use QR codes to tell the app what to do. If it's going to be a scientific instrument, or is it going to be an analyte-specific instrument? This is really closing the gap between science in the lab and science that you could roll out to, I want to say, preclinical trials. If you say clinical trials, that's a certain level, but it definitely shows you that we can go from science to useful data very quickly with this platform. Now, when it comes back to wearable biosensors, let me just sort of bring it back slightly and just kind of say, when I'm talking about wearable biosensors, I'm imagining that this is the skin, the epidermis, the outermost layer of my skin. And often we're trying to get through the dermis to the subcutaneous tissues. What we're trying to get to is the ISF, the interstitial fluid. And so, we'll either get there through a wire. So when I held up this sensor earlier on, there's actually a little black wire poking out the bottom of that. Abbott would refer to that as the filament, but that's basically an enzyme sensor that's going into the interstitial fluid and for them monitoring glucose. We can get there with microneedles. This watch is using microneedles. Microneedles are harder to see because they're generally 1 millimeter or less in dimensions. So we do have microneedle technologies. We also have sweat analysis technologies. just out of interest, it's not that easy to get always to get people to sweat, by the way. So be careful about this idea that I'm going to do sweat monitoring. Take it from somebody who's done sweat monitoring. It's quite hard to sometimes get people to sweat. And then there's also implantable sensors as well. So just a side note that at ZP, we are quite active in measuring lactate in various ways on people, but including sweat. We use our technology stack where we have electronics, we have Bluetooth connection, and we have the biosensors themselves, and we are able to essentially monitor lactate. Whoops, I went a bit quick then. Measure lactate in people who are working out. This is not a dead science for us. We're constantly working on technologies for collecting liquids from the skin, and I generally think, you know, this, I know companies that have done it. This ZP is one of those kind of companies, but this is not necessarily easy work. In fact, this is a good example here. This is genuine sweat, and to kind of get these kind of sensors to, you know, collect sweat is actually quite tough. This is a different one where actually it's a transdermal sensor. So this sensor has actually gone through the skin, and I'm measuring the interstitial fluid. Here you can see several sensors. I think about 4 sensors being monitored on the human subject here. Sometimes the nice thing about humans doing human subjects is if you're kind of a director or a founder of a company, you can get very involved in the, you know, in the study yourself. You can't get employees to do this kind of work because they've got an employment contract, they have rights, but founders can actually get involved in this kind of work. So just a couple of case studies. Implantable sensors, microneedles, and non-invasive. So the first one here is an implantable. So this sounds crazy, but this is a CGM package from Zimmer & Peacock, continuous glucose monitoring package from Zimmer & Peacock. We also do it in a cortisol format as well. And this is actually being put into fish. This fish is not dead. It's actually anesthetized. These fish are just swimming around in, I think it's called a RAS system, a recirculating aquatic system. But they've actually got biosensors in them, and the biosensors are continuously sending data out. And so here we've kind of got the continuous measuring over 9 hours, and this is where the fish were fed, and this is where their glucose levels jump up. Very tough engineering trying to, again, it is when I sort of say that point of care diagnostics, you know, coming up with a POC, this is a point of care diagnostic device as opposed to a wearable. You know, just that description about putting the sensors inside of things and continuously sending the data, you can appreciate actually how tough that really is. When you just make a measurement, you get the result, and that's the end of the sensor. That is easier than trying to do continuous monitoring. But as it is, we are very involved in putting biosensors eventually back into people, but at the moment it's a very kind of veterinary application. But we do have a technology stack, including electronics, for allowing people to do implantable and wearable biosensors. Now, Sensionics is, you know, has proven to us that the FDA will accept wearable biosensors. Sensionics has a sensor that goes transcutaneously underneath the skin. It's put there by a sort of a minor procedure, and the sensor at the moment does have FDA approval. It does lead to this slight marking, and this marking is because the sensor is inserted. It's kind of torpedo shaped, and it's got a material on it called dexamethasone, which stops encapsulation of this sensor. Whenever you put something into the body sees it, it recognizes it as a foreign object and tries to encapsulate it. To stop that, they've put dexamethasone on it. But what that's meaning is that this device is actually not being encapsulated. It's actually migrating. And when it migrates, it ends up kind of causing these kind of tunneling effects. And these are the marks that you then get on the skin. At ZP, we're also very interested in microneedles. We've been working on microneedles since about 2018. We have 50 patents on microneedles, and most of our technology is about glucose, lactate, and ketone monitoring. Our business model is actually, we are looking for well-funded companies that can genuinely afford to help finish this development, because this kind of development, I mean, I just reeled off some numbers earlier on. BioLink, 154 million. Dexcom probably 1 billion. So it's a very expensive effort to actually bring any kind of CGM type technology to the market. There's also non-invasive. Now the FDA really had to put out a warning because I was going onto Amazon and just putting non-invasive glucose monitors, and I was definitely getting hits for it. And it's interesting actually because I was at a conference where somebody showed the data from a non-invasive CGM, and the data was basically cyclic every day. They get exactly the same profile. So in fact, the entire watch, all the watch was doing was it was programmed to give a glucose profile, not reading one. It's just spitting out a glucose profile, and it day after day after day, exactly the same profile. So that confirmed, we knew that it wasn't right. The FDA then had to put out a warning and say, look, just because you can find these claimed non-invasive glucose monitors, unless they're breaking the skin, it's probably not. They have to be careful with their words, of course, because they're a federal institution. They don't want to get sued. But they have kind of put out a warning saying, look, unless the smartwatch is associated, you can have smartwatches that talk to CGMs like this, but this kind of CGM actually breaks the skin because it's got a little filament on it. So they kind of said, look, unless it's breaking the skin, it's possibly not working correctly. There have been attempts at non-invasive glucose monitoring. We've got Cygnus with a glucose watch. People kind of tell me about this glucose watch. I'm like, no, I remember the glucose watch. Don't tell me about it. I remember it, honestly. I mean, the glucose watch started in the 90s. It was launched early 2000s. So there's the glucose watch, there's Pentra, which less people have heard of, and there's also Apple, which I will talk about a little bit today as well. So the glucose watch actually comes from a company called Cygnus. There we are. It was approved by the FDA in 1999. It was worn on the wrist. It gave a reading every 20 minutes. It had an operational life of 12 hours, but it had a warm-up time of about 3 hours. And they also required calibration. So when I did that finger stick with this glucose monitor earlier on, or that that finger stick test, or finger prick test, I should say, it required that. And what they were doing was taking the reading from the glucose meter and using it to help calibrate essentially on the person what their actual glucose reading was. So they were doing like in-field calibration. In the end, well, not in the end, they were actually using a technology called reverse iontophoresis. There are several companies still, now that these have kind of come off patent, there are several companies trying to do reverse iontophoresis, where they kind of take these electrodes, they apply a voltage, try to pass a current, and the current is basically drawing ions out of the skin. And it's also trying to draw, with the ions comes water, and with the water comes glucose. So this is a theoretical way of getting glucose actually out of the skin, and then they can read the solution that's drawn out with a separate circuit. They are doing what's called a generation 1 glucose sensor, or at least they were at Cygnus. I'm not going to dive into generation 1 versus generation 2 today, but I definitely have plenty of videos online about that. The way this device actually worked was they'd have what's called a duty cycle, where they would actually apply a current for 3 minutes. They would then read the solution that was drawn out for 7 minutes. So they're probably integrating the signal. Then they would reverse the polarity and draw or pass a current through another electrode and draw a solution out of that and measure it for 7 minutes. So they were flip-flopping between two electrodes, drawing for 3 minutes, reading for 7 minutes, drawing for 3 minutes, reading for 7 minutes, drawing for 3 minutes. And what they would actually end up doing is averaging the signal. The problem is they were averaging this signal over 20 minutes. So you can understand that if somebody's glucose levels are dropping and you're averaging a signal, one that you recently took and one that you took from the past, you're basically, you're not telling somebody what their current glucose is. You're telling them what their glucose was about 3 minutes ago, plus what their glucose was about 7 minutes ago. And in a situation where somebody's glucose is changing quite quickly, you've got an inherent inaccuracy in that, because you're loading your number that you're giving them with data from the past. So I've calculated that, in fact, just inherently that could lead to something like an 18% problem with accuracy. And then the user feedback was people didn't like reverse autophoresis. It seemed to be itchy. It took about 3 hours to warm up, so they would wear it for 12 hours, but for 25% of the time, it was actually 20% of the time, rather, it was warming up. It was inaccurate. And so there was, a review done, and in the end, they were pioneers and they should be applauded for being pioneers and being real true innovators, because who would have thought of that? But in the end, it wasn't successful. There was another less known attempt at doing non-invasive glucose monitoring. There's a system called the Pendra. That was actually, I think it was Dutch. Yeah, it's Dutch. It had a problem with accuracy, and it had a problem with accuracy, and sometimes it was inaccurate in the least in some of the worst cases. I've got here something called an error grid, and an error grid kind of says to you, if you're different from the reference system, it's okay sometimes sometimes error is okay, but if the error is gross and if the error leads to the wrong clinical decision, it can be dangerous. And so an error grid allows you to kind of assess, even if I have an error, um, let's say my glucose was 5 millimolar, but in fact I read it at 6 millimolar. That kind of error is dealable. You can deal with it. The problem that will come about is if my glucose reading if my true glucose is 4 millimolar, and you tell me it's 10 millimolar, that's what we call like a zone E error, and that's because I could take some action on my to bring my glucose down, but in fact, my glucose is already down. It's already at 4 millimolar, and that could lead to my glucose going even lower. So that can be kind of dangerous. Um, so they had errors, and they also had gross errors. Now, they were trying to measure glucose through bioimpedance. Now, what they were really doing was actually measuring the sodium chloride levels and then trying to correlate that with glucose. That's a really tertiary type of signal, not a primary signal, not measuring glucose directly, not measuring glucose indirectly, but measuring glucose almost like indirectly, if I can put it that way. But it was, and they had problems with temperature and moisture. Anyone who's measuring on skin, you can understand temperature and moisture. They also had a problem with perfusion. If I'm running around, my blood flow changes, and their signal apparently was changing as well. In the end, this was also not successful. Just to kind of say that if you're getting into continuous glucose monitoring, there is something called the surveillance error grid. David Klonoff was one of the sort of co-inventors of the surveillance error grid. So there is a modern way of assessing your CGM or your iCGM technology versus things like the glucose strip. Now, Apple have also been working on non-invasive glucose monitoring for quite some time. Unfortunately, Steve Jobs in the end died of pancreatic cancer, but the first time he got pancreatic cancer, he also became a type 1 diabetic, which probably really woke up his interest in CGM, continuous glucose monitoring. And so, in fact, they've been working with various companies over the years. The latest public note that I know about this is that in January 23, they were working with TMSC on photonics. So they're trying to basically measure glucose through the skin by. I've got an Apple Watch here. Let me just grab it. Oh, in fact, that's not an Apple Watch. That's an Android watch. Here's an Apple Watch. The reason I bring up the Apple Watch is because there's clearly a couple of LEDs on the back here. They use these for kind of all sorts of various functions. But I think what they're possibly trying to do with those LEDs as well is it's ironic because I realized that this Android watch also has LEDs on it as well. So they're kind of opening themselves up to potentially trying to do glucose as well. Now they're obviously using these LEDs at this moment for measuring pulse. That said, I've read their patents at Apple, and they're trying to use infrared spectroscopy to measure glucose through the skin. And they're using shortwave and medium wave infrared. This is in public domain. Just to say that every single part of the electromagnetic spectrum has been tried by some company or other for measuring glucose. This is as old as the hills. For as long as I have been doing continuous glucose monitoring, there's always been a company somewhere that's claimed some magical part of the electromagnetic spectrum, be it microwave, be it Raman, be it infrared, be it I think radio waves. It's all been tried and nobody's so far been successful. Now I think they're not, so with Apple, they're trying to fire essentially photons through the skin, get the photons reflected back, and then foresee the glucose in there. The problem they have is that glucose is a little bit non-specific in its infrared spectrum. There's also a problem of chemistry. That's to say that sort of blood is 55 molar. Sorry, the water in blood, which is also infrared active, is 55 molar, where glucose is something like 5 millimolar. So you've got 3 orders of magnitude. In fact, 4 orders of magnitude difference in the chemical compositions there. You've got a quantum problem, as I say, that lots of molecules are infrared active. So if you look at the glucose infrared spectrum for glucose rather than the infrared spectrum for glucose, it has lots of activity, but so does the infrared spectrum for water. So does the infrared spectrum for, I think this is aspirin. I've just used this as a kind of generic organic molecule. But if I overlap all of these, it's basically just trying to make the argument that there's nothing super special about glucose when it comes to the infrared spectrum. Unlike hemoglobin, where hemoglobin, is a classic, you can kind of do a invasive monitoring of it. It's because glucose, hemoglobin rather, has iron in the +4 oxidation state. It's quite an intense, unusual molecule, but glucose is not that unusual. It's just got carbon, hydrogen, and oxygen in it with single and double bonds. It's like a whatever molecule. It looks like a lot of other things. They do also have this dilution problem, that the glucose is actually quite low concentrations relative to lots of other molecules in the body. And then you also have this thing that glucose is not unique in its ability to have an infrared spectrum. And in fact, water and all other molecules also have it. So I did a sort of back of the envelope calculation, and I have a suspicion that in fact, at least their signal is 1 and their noise is 2,750 at least. I try to be really conservative with that claim. I suspicion it's actually orders of magnitude different. Now, my argument sometimes, people say, well, when will non-invasive glucose monitoring come? I have a super suspicion that Apple's probably spent at least on the years about 100 million per year on this over a good 10 years. I don't have any inside information on that, but it's just knowing the size or having an estimate on the kind of group size that they actually have on this. So they have a problem with specificity, they have a problem with signal to noise ratio, and they have overall, but they carry on working on it. So I'm going to do a kind of summary of this. Now you can understand there's been a lot of content in this, but trends in the market are this: that everyone wants to decentralize test, not just in the healthcare industry, but in the food test industry, water test industry. Decentralization kind of, it simplifies the whole workflow. If a doctor or the patient can make a measurement and take some action, that's simplified the workflow. If I have to take a sample, send it off to hospital, get the results some days, weeks later, then it's often too late to really have a sort of meaningful necessarily impact in that particular case. So everyone wants to miniaturize or make it wearables. One of the best technologies for doing this, in my in my opinion, would be electrochemistry. Hey, look, these blood glucose meters are not so successful because of some love for electrochemistry. It's because they actually work and they have lots of features that make them commercially viable. I did a quick demonstration of a point of need diagnostic. It was all live, and I got the results on my phone there and then. So I would always say, if you've got a choice, go for point of care / point of need before you go to wearables. Wearables, it easily costs $1 billion to get to market. And with wearables, there are lots of configurations, from wires like the Abbott Freestyle Libre 2, microneedles like ZP has, sweat sensors, and implantable sensors. And then you saw those kind of case studies of where we're putting biosensors actually into fish and pigs. We're putting microneedles onto people using this watch format. But there's also some lessons to be learned from the past, from Pendra, from Cygnus. I think the lesson there is, reverse autophoresis is not straightforward. There are people trying it. There are people trying it in the past. There are people who have tried it recently and given up. Bioimpedance, measuring the impedance of the skin and correlating that back to glucose, feels like a very far stretch. And you will always on LinkedIn see new companies popping up who claim to have solved the non-invasive glucose problem, but there are very large companies who invested a good decades and a half on this, putting in significant amounts of money and haven't yet been successful. If you do have any questions about ZP, ZP really is our business model is contract development, contract manufacturing of point of care diagnostics and wearable biosensors. So if you have any kind of commercial questions around this, don't hesitate to reach out to us. Okay, thanks very much.